Hello everyone. In this video we will continue our examination of topic 2.1 motion, and in particular we will begin to discuss acceleration. So, just as velocity is formally defined as the rate of change of position with respect to time, where the average velocity is delta x over delta t, the displacement over the time. Likewise, we can define a quantity that concerns how quickly the velocity itself is changing. And in fact, this quantity is known as acceleration. So acceleration, written as A, with a vector at here, is the rate of change of velocity with respect to time. This is the definition of acceleration. In calculus notation, the instantaneous acceleration is given by dv dt. But for everyone without calculus, the average acceleration is given by the change in the velocity over the change in time. So this is an equation we're going to use quite a bit in this class. Notice that we are going to have some acceleration, whenever there is a change in velocity. And so there are three ways we can accelerate in physics. Okay. It's important to recognize that acceleration, the word acceleration in physics means something different than it does in everyday life in vernacular English. Normally, when we say the word accelerate, we mean one thing. We mean speed up. And while speeding up is a formal way, or is in fact a way in which you can change your velocity and is therefore part of the physics definition of acceleration, it is not the only way to accelerate. According to the physics definition. For example, when you are slowing down, you are also changing your velocity. And so you could accelerate simply by slowing down. That would be a case of acceleration. And notice if you were to slow down more quickly, so if your rate of slowing down was larger, then your acceleration would be larger as well. A technical term that always means slowing down is deceleration. So deceleration is a word that means slowing down directly. And finally, there's one more interesting way in which you can accelerate, and that is by changing your velocity, by changing the direction of your velocity. So notice that if you change the direction of your velocity, then even if you don't change your speed, which is entirely possible, you can be accelerating. And we will see this in a later unit in great detail. So one of the ways to accelerate is to change direction. Or you could do some combination of changing direction and slowing down, or changing direction and speeding up. All of those things are reasonable. So take a case of an object, as shown here using what's called a motion map, where the object is speeding up and then slowing down. Okay, speeding up and then slowing down, engaging in acceleration in two different directions here. When we represent that, we represent the position at equal intervals of time with a dot. That's shown by this black dot here. And the velocity is shown by these blue arrows as they grow and increase in magnitude. That's the speeding up part because that velocity is increasing. And as they decrease in magnitude, that's the slowing down part as they decrease in length. Notice that the way the acceleration works is that the acceleration can be used to represent sort of the change in the velocity. So you can imagine applying this little acceleration arrow to every velocity vector here to get the next velocity vector. And each time this constant acceleration adds to the velocity vector, and then in this region, the acceleration subtracts from that velocity vector until the object comes back to a stop. The unit of acceleration is meters per second squared, or meters per second, which is how I would recommend you begin to read this unit out in your head. So usually you want to write it like this, but I would strongly recommend that you read this out in your head as meters per second, and it will help you keep track of what acceleration really means. So for example, if you have an acceleration of positive 3 meters per second squared, what that really means is the object is changing its velocity plus 3 meters per second for every second of travel, okay? So if it starts out at a velocity of 0, if we're taking a look at this motion and we examine a data table for it, then at t equals 0 seconds, the velocity is 0. At t equals 1 second, that velocity is plus 3 meters per second. At 2 seconds, the velocity is plus 6. At 3 seconds, the velocity is plus 9, and so on and so forth. So the velocity is changing by 3 meters per second every second. That's what the acceleration means. Then right at t equals 4 seconds, the object doesn't stop and it doesn't turn around. It just starts to slow. So this is not a turning point, okay? The object starts to slow. And the object is continuing to go forward, positive 12 meters per second, positive 9 meters per second, positive 6 meters per second, positive 3 meters per second, and so on and so forth, where the acceleration is negative 3 meters per second for every second of travel. So we started out at 12, and we are losing 3 meters per second of velocity for every second that we are traveling. And in fact, if this continues to this point right here, then at t equals 8 seconds, right, that velocity strikes 0 and then becomes negative. And so t equals 8 seconds would be a case where the object in question turns around. Notice that if we're plotting position versus time or velocity versus time, you can see that we're speeding up in this region for position versus time and then slowing down, finally coming to a stop. And here we have a high positive velocity going faster, going faster, going faster, going faster, slowing down, slowing down, slowing down, slowing down.